This is a huge value added as compared to what we just saw when Nate was talking about some of the last tests there, what I euphemistically call dumb ground, because for what you'll see here, the sophistication is amazing. We're kind of going from the Wright Flyer to the space shuttle. All right, why is good grounding important? We've covered quite a few of these things already, but notice I said good grounding. And the reason for that is because the past years, for many decades, the thought was take a ground rod, you pound it in the ground, you make your connection, and that's all that needs to be done. In today's sophisticated distribution and control systems, good grounding is key. You can't just think about it as just putting in a ground rod and then forget it. As Peter was talking about earlier, when you capture that strike and you bring that energy into your grounding, I call it inviting the devil into your house. Your grounding is key because all of the distributive control systems are now operating on what? Microprocessors. Many of the same things that are in your high-end televisions, stereo equipment and such. That energy into the grounding system can disrupt that grounding system, and if it's a high enough voltage or a high enough, what we are going to be hearing a lot about is impedance. You put in a high current into a high impedance, results in a high voltage, and that will destroy some of these systems and bring them offline. Many times what you'll go onto a facility, right when you're walking into the facility, they'll have something that says lost time event. One of their biggest things that they are concerned of is making sure they don't have any type of lost time event. Lost time means lost revenue. So we are mostly going to be focusing on, for the most part, on power utilities. That's where most of my experience is with this. But it can be used in just about any type of grounding scenario. If you have a customer that, we've done it for banks, military, data centers, just about any type of grounding system this can apply to. All right? Our key thing here that we're looking at is personal safety. This is one of the major reasons I am brought out to analyze a system, is because a customer will wonder, when a worst case fault happens, when you have a power line that falls to the ground, and very often these things are very high voltage, and they can inject anywhere from 20,000 to 30,000 amps into the ground, which is very similar to a lightning strike, except the lightning strike only lasts for a few microseconds. This can go on for many seconds, depending on how quickly they can clear that fault. Well, all the personnel that are going to be in that area, what is going to happen to them when that fault occurs? And this is what Smart Ground can answer. So, critical parameters. We talked about soil resistivity. That is one of the key parameters we got to look at. Impedance and resistance to earth. This is what the fallout potential test that he was talking about. When you have a large facility, it interfaces with the actual earth. How good of an interface is it? You can't really tell unless you go to do something similar to the fallout potential test, but we're going to show the standard method has its faults in there. Continuity and common bonding. You have a facility, maybe a customer that has a facility 20, 30 years old. They have no idea about the integrity of the grounding system. How well are the cables under the ground connected? So we were talking before about soil resistivity. The better that soil resistivity, or the lower it is, better. But that also means that soil is more corrosive. That copper underground, what are they going to do? Dig it up to take a look at it? They can't do that. They can't even do that really with a standard meter. With a smart ground meter, you can actually determine the integrity of the ground connections. And then key things here is the step, touch, and transfer voltages. This is what we were discussing about what happens to personnel when that worst case fault happens. If somebody is touching something close by, or if there's step, how far apart it is in that resistance, what is going to happen to your body circuit? Because your body has a lot of electrolytes and salt in it, and you have your own little power generation here. Are you going to have a heart attack and die? So we're not talking about, you may not be hurt, or you may be hurt, but the key thing is to make sure you survive. So these here are guided by, here in the US, the IEEE Standard 80, Guide for Safety in AC Substations. Internationally, we're looking at IEC 60479, or sometimes it's called IEC 479. Please let me know if I'm talking too fast for anybody. Sometimes I have a tendency to do that. All right, so your measurement devices, the traditional method that Nathan had spoken about a little bit, it's a standard ground resistance tester. A newer method that came out is a clamp-on tester, and then our modern method is a smart ground test. All right, this utilizes advanced computer modeling, and it is also EPRI approved. So next question is, who or what is EPRI? They are the Electrical Power Research Institute, and it all says it in the name. They're basically a research and development group filled with scientists that they focus on all things with power generation, delivery, and management. They worked with the developers of the software and meter to address the situations and shortcomings with the other types of meters. This meter is now, or this method, I should say, is now actually called out for in IEEE Standard 81 on methods on how to test. So if you have a customer that's asking about things, this is actually called out in the standard. All right, so this was developed in the 1930s. Basically, your power grids and power needs were much smaller then. So you didn't have to have a meter that created much power. It was less congested, less noise, and by noise what I'm talking about is noise being developed actually traveling through the earth and also overhead. Used to measure resistance of electrode or a grid, so resistivity and continuity. It's had its time and place. Shortcomings. We were talking about this a little bit with Nate. The ground system to be tested must be de-energized and isolated. That is a huge problem. How are you going to tell a utility, by the way, guys, you need to shut down completely in order to do this test accurately? They're going to tell you to pound sand. Excessive lead lengths require to measure large grids. You remember when Nate was saying you have to have longer lead length. The larger that facility gets, the larger that ground grid gets, the larger that current return probe and also the voltage probes. Well, those probes, they are subject to the electromagnetic interference, EMI and RFI, that's in the atmosphere and the ground. And they act like an antenna. So what you end up having is they can be adversely affected by that noise. What happens when you have adverse effect of the noise? You have a low signal to noise ratio. That results in errors. Instead of you getting accurate readings, you are getting bad readings. The test results have unknown confidence factors. You have no idea how well the accuracy of the test is. So if you are creating, or if you are trying to formalize what is the danger to the personnel in your facility, how are you going to do that if you don't even know what your error is? This is where the smart ground test comes into play. Minimal to no self-diagnostics on the test equipment. How do you remove human error if it's been caused? How do you know if it's even there? So, citing all of these shortcomings, this is not practical in modern facilities anymore, or in this day and age of litigious society. If you are an engineer and you've developed a certain grounding system saying it's safe, and then somebody dies, there's going to be some type of lawsuit. I'm not going to go into this much. The key thing to think about this with the grounds, probably a lot of people have seen this. It's used quite commonly in places to go and test certain ground wells. And I see them a lot in power stations. But the problem is they seem to be user-friendly, but they can only be used in a very specific way. And quite often, most of the time, they are used incorrectly. So it has a few criteria that must be met, but quite often you can't place the meter in the right place in order to get a proper reading. So, smart ground testing. It is comprised of essentially a combination variable frequency current source and 6-channel data acquisition platform. All right, it consists of the meter, and here's the key thing here, this software, Windows Integrated Grounded System software. And why this becomes important, you remember when I was talking about low signal to noise ratio? This will go out to 0 to 500 volts and up to 15 amps. Many of the other types of meters are very low voltage, and they test at one single frequency. Why does that become important with the multiple frequencies here? This allows you to test for impedance. Does anybody have an idea what impedance is versus resistance? Okay, impedance is similar to resistance, but it has to do with, let's say, a moving or an alternating frequency or alternating current. So think of a hose going through, water going through a hose. It trickles through that hose very well. But if that water was suddenly reversing constantly, going back and forth constantly, that resistance increases because you're actually running into the other atoms in there. So I can't give you an exact analogy, but it's essentially what occurs is we are testing at AC power. So resistance is not the key thing. AC is an alternating frequency. You need to know the impedance. Lightning is an alternating frequency. If you look at it very closely, you need to know the impedance of the system. When you have high frequencies or multiple frequencies, this is similar to also having, instead of just one picture of your grounding system, you have many thousands of pictures. You can develop much more information off of a system like this. If anybody has any questions as we go along, please shoot them out. All right, so the software was originally developed to assist in the actual design of grounding systems. After the developers had made this, they realized along with EPRI that they can use this type of testing to also find problems or use as diagnostics. It was developed by Dr. Miliopoulos and Konkanides, and these two gentlemen are professors over at the Georgia Institute of Technology, and they also sit on the IEEE Standard 80 board. All right. Your meter has 11 different test functions. We typically use 3 for most of our testing. But the key thing here is the analysis, the ability to do this with the software. Our step, touch, and transfer voltage, which we've talked about a little bit. A steady state analysis allows the facility to know under normal conditions or under normal operating conditions, what is the grounding system, how much current is going in the grounding system, which allows them to know a little bit more about if their loads are imbalanced. All right? Lightning shielding analysis. This becomes very important, can become very important for you here because this could possibly be an entrance into getting dissipation array systems into a facility. The reason being is because what this will do here takes into account a 3D model of the facility. Okay? All fences, structures, power lines, what have you. The computer will do what's called a rolling sphere analysis. And it comes up with a statistical analysis of how many strikes per year a facility can expect to have on those structures. So if you know which areas are weak and where they need protection, that allows you then to hopefully go and also say, by the way, we can help you with that. Here's where you need to have DAS on these structures. The transient analysis, this one allows us to determine between certain areas how high of a voltage can be made from a lightning strike. All right, and we'll go into some of these a little bit further. So we call it a smart ground audit, smart ground test. There are 3 typical tests that we do, and 1 or more of the analysis can be added. But typically we'll have a soil resistivity test, a ground impedance test, and a point-to-point measurement. And then the step, touch, and transfer voltage to worst case fault. However, we can develop this to whatever you would like. We sometimes call it a smart ground light. I'm about to go on one where all we're doing is point-to-point measurements to determine the integrity of the system. We have already been to that site, so this is actually our second trip out to the site, and they just actually delivered another PO to us to do the large area. It's international paper. So they're looking to us to do multiple tests at that site. So the methodology, typically we'll build an electrogeometric model. This is both a 3D model and a system network model and the ground model. We'll do the measurements. We'll analyze and assess the conditions, provide recommendations, and prepare the report. And again, this can be customized to whatever your customer's needs are. Okay? So, system network model. What this represents here is the ground under test would be, let's say the facility that we're looking at is actually represented by this icon. This then represents the transmission lines of the system, not just the ground system that we're testing, because if you think about it, all of these transmission lines here, what are they, essentially? You have these long these huge metal towers, and each one of them has a ground rod at them, or multiple ground rods, and they're interconnected by usually what's a shield cable over the top. So that's all part of your electrical network, or your system. These different transmission, what's represented here, can be thought of as multiple resistors into the earth. So it's not just your grounding system here. We are talking about a complete system where these could be miles away from each other, and then each one of these are other substations or the generation station. So you're starting to get an idea of how the modeling capability of this is, because what happens is we will go in and not only just model, let's say, just this facility, but if you clicked onto these icons, depending on the type of tower, even the type of shields and the steel and the type of conductor, that all has an impact on your overall impedance. And this can model that. So this is, you've seen these type towers. There's many different types of towers. How these cables are hung in comparison and the geometry of how they're put on there and the height off the ground, all of that, even how well, the span will all have an effect on the impedance of the system, which then will have an effect on your grounding system in your facility, which then in turn has an effect. If you have a fault, what will happen? It affects the whole, everything affects, it's all like a domino effect. This is basically a system network model now in kind of a one-line diagram. So you have your power generation facility, your substation, the power lines that are going out of it, and then your grounding system that connects the two of them together. And in here, what you're not seeing is all the breakers and nodes here, how they're interconnected. How do I get that? Well, I'm going to be asking you guys for grounding drawings. This is the first thing I need to have. And believe it or not, I even have to sometimes piece them together to that size. I got a map one time a little while back from one of our customers, and I had to laugh because I was thinking, oh wow, this guy really put this together, and I had to spread it out in that manner. But essentially what happens is we'll take something like this. We prefer electronic format, of course, and we have these in electronic format, but in order to really understand the size and capability, sometimes we have to go to this level. But we put it into the ground system editor of the software, and we develop the ground grid. So these are actual substations and such that we have used. And you can here's one that originally started off on one side, and then they started expanding the ground grid. So this here would be kind of like the substation and such. And then we have transmission towers as they exit. Inside that substation, what is it? There's a lot of equipment. You have your transformers or the major pieces of equipment, breakers and such. There's a library within the software that will allow us to put in the different types of transformers and what I need to get when I'm out there. This is the nameplate off the transformer, which will allow me to adjust the impedance and the impedance factors in the software. So some of this is done pre-testing. We go out, test, come back, and adjust the model. Here's you remember the ground drawings I was showing you earlier. We will also lay this over any type of satellite images and adjust it to scale. And that becomes important later on because we even use GPS within this. So this is a facility that we out in southeast, where they were having some issues with lightning tripping the facility offline. And we can get to this a little bit later, but essentially you're looking at about a quarter mile between the substation and the actual generation facility. And here's your 3D model that would be used, let's say, for the transient analysis or the lightning shielding analysis. So measurements point to point. This is what is a low impedance continuity. This is the testing that will allow them to determine the integrity. Allow us to determine the integrity of the actual ground connections from one point to other points. Whether or not we can determine whether or not the ground grid is degrading, or if the connection is completely severed. So in the report, you will see all these points that we go out, and these are points we actually tested to. And each one of them, there will be a table that shows where the connections are and what the values that we got back. But we can even do this in a 3D method. Okay? So it's not just along this vertical. We can do this into a tower, where we found there was all types of, this was a customer that had problems, lightning striking the stack. It would bring down all the electronics inside the stack. We found some disconnections inside here, and we were able to make some recommendations because they actually were running the ground wire on the inside of the stack, metal tube in some ways that adds into the impedance, And so what was happening is the propagation of the lightning was not allowed to propagate properly just to ground. It was going through all their electronics instead due to the high impedance. So here is what I will typically see while I'm testing is these 4 background images. You remember this, if you can see that, here is the injected waveform. The key thing is what we're looking at here is the impedance, all right, and the phase angle. So what I'd like to see is a phase angle typically in the 50 to 70 degree range. I want to see an impedance. Here is the resistance, and if you notice, the impedance and the resistance are quite different. All right? What I would like to see when I know I have a good connection is that the impedance should match very well to the reactance. If you don't know, if you're not sure what these are, is essentially the reactance is what it sounds like is the reactance of the metal to the current going through it. All right. This allows me to, once I see this match closely to the reactance and I have a phase angle, I know there's a connection. So a false positive, can you imagine? Here's one out at a facility for an oil storage facility. We run out about 1,000 feet of wire. We do a test, and it comes back and tells me 25 milliohms. Doesn't sound like much. If you were to do a measurement, regular measurement, you would think that's a connection. It's only 25 milliohms over 1,000 feet of soil. But if you notice here, the impedance matches almost exactly with the resistance, but not the reactance. And my phase angle is very low. This tells me that what I'm really reading through is the soil. So any type of fault, any type of lightning strike, anything to that particular tank, that becomes a danger. So you couldn't do this with a standard test meter. It's just going to give you back a reading. All it's going to tell you is your resistance. It's not going to let you know your impedance or your phase angle to let you know that that's actually a problem exists in that point. You'd have to dig up the actual earth. So this is where it becomes an advantage for your customer to say, yes, it's a bit more expensive, but you're going to find out much more from this than you are going to find out from a standard test. So in the report, you'll have something that looks like this. All the test points, where they are, the computed resistance, the measured resistance, and the measured impedance. If we see large discrepancies, or even some smaller discrepancies, we can highlight those and say, here's where you have some issues. So in case in point, this was a facility that had a lot of their instrumentation wires going through here, but they also had only one single ground wire that attached this facility to the generation station. Many years ago, when the substation was only this little part here, that was fine. But over time, it got larger and larger, and they only had, so they didn't have enough or low impedance enough when a lightning strike, maybe outside here, to keep these two at the same potential. Everything should rise and fall at the same time. Standard meter would not have told them what they needed to do was not only to remove all the instrumentation and control wires that are running right next to the ground wire, because it couples over, any type of surge will couple over onto those instrumentation wires, but that they also had to add some extra ground wires. The recommendation came through, no problem since. So resistivity. All right, you saw Nate talking about it earlier, and we will put in multiple ground rods. Key difference here is your typical soil resistivity test, your typical meter has a 1-foot ground rod. It doesn't really inject a signal very deep. We have a 1 meter ground rod. This will inject over 350 foot deep. All right? You can see here, included in the report is the injected current, voltage current functions, probe transfer functions, a 2-layer soil model is developed, because soil is very rarely is it ever just a single soil sample. It's stratified. Typically, all you really need is a 2-layer soil model. Reason being is because if you have a customer that is putting in a power generation, you have a ground rod of a certain length. You need to know how deep do you really need to put that ground rod to get to that lower soil resistivity, especially if you're in a high resistivity area. So we'll do the testing and come up with multiple, we'll do this at 5-foot spacings, 10-foot, 20-foot, and 40-foot spacings, all at that same 350-foot depth. All of that information is then applied to mathematics to come up with a best fit model of what your soil is. And it'll give you a 2-layer soil model. So the measurement and the soil resistivity, again, with more sophistication, it'll actually tell me my percent error, gives me my resistance, and gives me my injected current. Note that the low current and high probe resistance in these here. This allows me to go back and say, I need to change something. This is the part I was talking about where the meter itself will perform diagnostics, will let me know whether or not something has to be adjusted in order to get better data. So here is what I can do. I went back, adjusted some of the parameters by either adjusting where the probes are at or realizing that I needed to pump up the voltage, and I can then get a higher output, and look what happens when the data comes back excellent, where we had sometimes acceptable and very good is all you can get, no matter what you do, you have to change it. But now we have a much higher quality of data. So our different soil resistivity measurements at 5 foot, 10 foot, 20 foot, and 40 foot readings. These are each one of them. And you can see it actually changes. Upper layer soil level and lower layer soil level at different distances. And it comes back, and then you get a best fit model to say, here's your 2-layer soil model. So in this case, the upper layer soil resistivity was 41.4 ohm meter, the lower level was 66.5, and it gives you how thick that upper layer is. In this case, they have some very good soil resistivity, and they're not going to need to necessarily break through that upper layer in order to get to a low soil resistivity. Ground impedance testing. This is where they get the most really out of this meter in some cases. I shouldn't say most, but very effective. We were talking earlier about the standard meter, and the larger the grid becomes, the further out you have to do your testing. Why? Is because you can't have any of your readings be influenced by what is going on in here, the signal and the noise ratio. So typically, rule of thumb with the standard meter is 5 times the diagonal distance of your grid. But as the grid becomes larger, it actually goes up exponentially. The larger the grid you can get out to 8, 10, 15 times your diagonal distance. Now, that may not sound like, well, what does that really mean? Well, I recently came back from a test we did in Mexico where there was one facility under test, but they were connected to 4 other facilities. The total diagonal distance of that was 1 mile. Huge facility. Am I going to walk with 15 miles of cable to get away from that in order to get accurate readings? Thank God I didn't have to. With us, still a lot in this case. With SmartGround, we only have to do 2 times the diagonal distance. So yes, I had to have 2 miles of cable for the current return probe. That's an extreme. But I'm just trying to say 2 miles versus 15 miles. Usually, I only have to take the current meter like this a few hundred feet out, whereas in this case, I may have had to take 5 times out. We'd be off the screen. We have our multiple probes here, whereas instead of a fault potential test, instead of just the 2 probes there, we have multiple voltage probes where we can get over 260,000 data points for this one test. Here is an example, once again, where the meter tells me, yes, if we were just doing this under a standard test, yes, you're going to get a reading. But you see this right here, this representation, all of this? This is your 60 hertz noise, your 120 hertz, 180 hertz. These are all what are called harmonics of the fundamental frequency we're testing at. This is all noise that would affect your standard meter and all the cables. Remember I was telling you, all those long cables, they're like an antenna, and they have a low amount of power on it. So what occurs here is you're not really reading what is being injected into the earth. What you're reading is what's being coupled onto the cable. So your readings are off. If you are a safety manager and you're trying to develop something, a protocol for it, and to determine how much copper you need to have in the ground, or to determine how safe your facility is, well, you've heard the old term, garbage in, garbage out. If you have a test meter that you're only getting garbage readings, and then you're going to do calculations, and based on those readings, well, the calculations are worthless. So here you go with this. I can go back, adjust my parameters, double my, in this case, what I ended up having to do was double my data acquisition points, turned up the voltage, and this is what we end up with. Same facility and much better data. Whereas before we only had 48% or 49% was valid, now we're in the 95% of the data was valid. All right, so we eventually get to what we really want is the ground impedance. In this case, that facility came in to 109 milliohms or 119 milliohms for the entire facility. Far less than 1 ohm. So you remember when we were talking about standards, they bring up 5 ohms, 1 ohm. That's typically for a ground rod. There isn't a standard necessarily for an entire facility. But what we want to do is find out what that resistance is going to be. This can be considered, if that whole facility was 1 ground rod, this is their resistance. So we take that then and run it into assessment to determine what the danger is to the personnel at the site. We will put in the parameters, whether we're going to do this to IEEE or IEC. We find the worst case fault. In this case, the worst case fault is, wait, I'm going ahead of myself, sorry. It tells you here what your permissible touch voltage and your permissible step voltage is based on the duration that the facility has set up, saying how long will it take for a fault to clear? In this case, a quarter second. That doesn't sound like much, but a quarter second when you have 20,000 amps coursing through you is a lot of time. The facility is modeled, and in this case, it shows us worst case fault. You see that kind of like a little, what looks to be like a little lightning strike? It determines, it goes through every different fault scenario. This happens within a matter of minutes, and finds that the worst case fault is a line to neutral fault at this bus fault location here, and it will deliver approximately 13.5 thousand amps. All right, that's for this facility. Here's a facility where we're looking at the same thing, and they're looking at maximum touch voltage, 116, allowable touch was 170. So this facility actually passed the testing. However, we do run into facilities where, in this case, the customer had us come out. They had their personnel that every time they touched the ground wire or anything, like they were getting shocked when they were inside of the facility. Well, that actually occurs quite often because when you're walking under power lines, your body is a capacitor and it'll charge a little bit, and you touch the ground, well, you're going to get a little bit shock. This facility was built way back 1940s. The power lines is 470 kV, and they were actually a little bit low, so the personnel were very much inside of that electromagnetic field. Here, what they were looking to do was expand here. They wanted to add another 230 kV line. Well, we came back to them, hey, you can't even do that. Your existing parameters are way out of touch. Their allowable touch voltage was 889. This means allowable is for someone to survive. They will not get a heart attack. They may be injured, but they will survive. They're looking at 4,625 during a worst case fault. You would not be able, again, what does this mean to you? The customer is not going to be able to tell that with a standard meter. They're not going to get that. So within the safety analysis, we come up with areas that are dangerous for the people to walk through. And these are kind of a legend for the areas that tells them what voltage that they will experience, either under a step, in this case, a touch voltage. Strike risk analysis. This is the lightning shielding analysis. Remember what I was talking about? We'll start off with a 3D representation of the plant. We put in all the different types of structures, stacks, tanks, control houses, cooling towers, what they may be. A rolling sphere method is determined or is developed based on whatever method the customer may demand. And it comes up here with all structures that this place can get. Well, it's going to expect to get approximately 1 strike every 2 years or so. 1 to 2 strikes. And this is how many each facility or each structure can get. So now this lets you can let them know, here's your weaknesses and possibly then an inroads to putting DAS in. Your transient analysis. This was a nuclear power plant. They were having problems with surge problems with what they called their vacuum building in this area. We simulated a strike to a lightning rod in this area, to see what the voltage would be developed. And this represents your first, like say, microsecond, and then as time goes by, out to 10 microseconds, how that wave propagates. And we can determine what the voltage will be in the area between, let's say, the control house, which was in here, and the vacuum building. And this shows them how many kV of a surge will be developed. So the specific recommendation will be dependent upon the results from all of our testing. Perform the same analysis on the system as in task 3, assuming the recommendations have been implemented. We even have a bill of material that comes along, a basic bill of material that comes along with the recommendations. And we can then rerun the analysis saying, if you implement these, here's how your system will work. And these are actual case studies here where we recommended them to lay in some more copper, but not only that, but to put some counterpoise out to the first transmission lines. Now, what you're not seeing in here is all the work that we had to do. We ended up, as many of you know, the transmission line companies are usually not owned by the same power company. It's another company. The substation might be owned by somebody else. So we ended up having to work with the power utility and all the other groups involved to come up with a scenario that they all would be satisfied. We ended up going 4 different iterations of recommendations to finally come up with this method here, and here's how they fell in line afterwards. Now, we were not called back out to perform the testing again, but we have been called out to other places where we have had, let's say, there was a power plant, they had a flashover, somebody was hurt, the power utility went down for months. It was their capability to generate power went down for months. A lot of litigation. We were actually hired by not the power utility, but by the law firm to go and do the testing and find what was wrong. We found a huge amount of discrepancies between what was said on the as-built drawings and what was actually done. Their recommendations were implemented, and we were called to go out and retest to make sure everything fell in line with what we had recommended, and it did. So smart ground testing is used quite often. SACUS is even, Dr. Miliopoulos has been used as an expert witness. This can be used to determine, we're scratching the surface in some ways. He was able to determine one time a little girl was shocked over a mile away from a power utility plant. She was out playing in a ditch. There was a metal tubing that was inside the ditch. A fault occurred at the plant, and the little girl was injured. Using this method here, it was able to determine that the transfer voltage was well in excess enough to hurt the girl. Final report provided and documentation of results, and all measurements will be included in the report. All right, and plus, there's always questions. So it also comes with a few hours of, if the customer has any questions, direct them back to us, and we can help answer any questions that they may have about the report. So what does this mean to you? What do I need to get started? Well, I have a set list that I can get you of information that I require. Key things are typically the site drawings, how many type of site, whether it's a substation, a chemical plant, GPS coordinates of the site. The reason I need that, I go onto the satellite imagery, and it helps me determine how difficult of a terrain and other things am I going to run into, or even how congested of an area to perform the testing. Technical information if they have a short circuit analysis. And then helpful is, what are the customer's expectations? What are they trying to find out? Are they really just are they just doing this for insurance purposes where they have to get a test done every 5 years? Or is this something maybe with litigation or something? I mean, that's why I put in there, are we doing something specific to even to a child's weight to determine what had happened to somebody smaller than, let's say, a standard human being? Because usually the testing for IEEE Standard 80 and IEC is relegated to, say, to a 50 or to a 75 kilogram person. So, somebody much larger than let's say a child, where their body resistance is not as high, and their susceptibility to a fault is much greater. So, full circle. I think the key things, we just went through a lot of information. Key things is what you got to realize is for your customer is tell them that what they will be getting out of this is much greater than their standard testing. You can get them in contact with me. You'll have this also to go through, okay? The key thing is when they will bring up the standard testing is that they will not be able to know what they're actually getting. They're just getting a number. What does that number actually mean? You know, what is the error? What is the confidence factors? So none of that will, if they're in a congested area, all that noise in that congested area, all the noise in the electrical system and the grounding will have an adverse effect. Garbage in, garbage out. There are other programs out there similar to Smart Ground. And I don't say similar because you may have heard of them. CDEGS is one. That's quite well known. The problem with CDEGS is it uses this input, the data is input from a standard meter. They go out with a standard meter and run the testing, and then they put all of the information into their computer program. But again, I'll repeat it, garbage in, garbage out. So if you have any questions, I mean, the key things are we can do this without having to shut down the plant. The meter itself, its algorithms will remove all of the noise. It returns confidence factors back to you and will tell you what your error is. Basically, really, this program is integrated, whereas some of the other programs are not. If you wanted to do the testing using CDEGS or something like that, you have to then do just that testing module. If you want to do testing on ground impedance, you have to do testing with a module that does that. It costs money for the different modules. Everything here is integrated into one meter and one program and allows us to get everything done at one time. Any questions? Yes, ladies first.
Is there an average, I realize this may not be an easy question, there's not a good answer. Is there an average cost to do?
I've done some analysis, and yes, it usually is in the range from, let's say, about $10,000 a day, maybe. Sounds high, but quite often we go out for multiple days to do testing, and some of the key parameters, some of the bigger expenses is the shipping of the equipment because it's about 1,000 pounds. So on average, I would say it's about $10,000 a day. Let's say for the full report and everything.
Is there an on average of how many days it takes?
Anywhere from 2 to 7 days, depending on the size of the facility and the scope of work. I can go out for just 1 day also, but many times, it's like if we're out there and you're having issues, let us take care of all this. We're not just trying to sell them. We really are trying to solve problems and get answers. Because we have had customers, they've said, well, no, we just want you out there for the day, and the next thing you know, they want us to come back. Well, now we got to go and ship all the equipment back out. We got to go, do these things. So it's best to get it all done at one point in time. Brian Doherty back here, he is by far, he's hiding behind the computer. He is our most prolific Smart Ground sales guy. Brian, can you stand up? Can you talk a little bit towards what your tactic is with the sale?
Well, as you and I discussed, a lot of times I use this as an entree. And we do a lot of paid surveys and go out and visit plants and customers pay us to come out and take a look at what's going on with their facility. And a lot of that's visual inspection. You don't really know what's going on grounding wise. There's a lot of buried under the ground. What we're concerned about is what is in the ground, not necessarily what's bonded and above ground, which you can physically see. So a lot of times in doing these surveys, the plant's got any age to it. Obviously there could be corrosion and so forth going on in the grounding system. If they're having ongoing problems with lightning and so forth, there could be problems with the grounding system. So a lot of times when I do initial interaction with the customer, is I always use a little bit of that, what they call FUD, fear, uncertainty, and doubt. And we don't really know what's going on in the earth. The best way to do that is through the system. Now, I've got a really good understanding of how the system works and how it compares to the other methods of doing the test. And this, by far, once you understand or get a grasp of how it does the testing, it's going to give you the most exact indication of what is going on in that grounding system. So I use it a lot of times as an entree. But having an understanding of how it works and being able to talk with customers, that's Lee and my other sales guy's job here to be able to do that for you. If you'd like to get to that point where you can at least get the customer, you pique his interest. Lee said it's an expensive, I guess you could say it's an expensive test. It's not once you really see what it is and what the result is, what you get from it. But it is a value-added proposition. You got to sell it to the customer. You can go out, take a fall potential meter, and have a guy run around and take some readings, and then you got a bunch of readings on a data sheet, and the guy says, okay, what does that mean? I don't know, it's a bunch of I don't know. This thing will actually just take it and put it into some format where you'll understand it, where the customer will understand it, and it gives you an executive summary, so if he doesn't want to read all that backup data, where these things end up being about 250 pages of the report, with all the test data in there, he can look at that executive summary and say, this is what you need to do to fix the problem. And you can go an extra step with that, and he can actually, if he wanted to, if they want to pay for it, we can model what will happen if they do those changes.
Yep.
We can tell them before they do any work at all, you know, what the results are.
Okay, I think what would be good is you have to do a comparison. We say $10,000 a day or so, but you also got to look at a standard test audit may be in the range, and I've seen this from competitors, of around maybe $7,000 a day. So we're talking about, you know, basically a small increment for the amount of information they get is huge. And also because the our competitors that will go out and run the testing, they will not let the customer know that they need to be 5 times the diagonal distance or other things in order to get the proper readings. I have seen, and I just came back from one, I was out of country, where they went to go test the grounding system, and they had an 80 feet of wire to do the ground impedance test. 80 feet. That was it. I'm like, and they're measuring it. Now, in this case, they were measuring tanks, each tank. Now, but each tank is over 350-foot diameter. So if you think of the ground rod, you remember when Nate was talking about the volume of influence, that 350-foot ground rod, which is essentially the tank, that is over 1.1 times its diameter. They're not even getting out of the influence of that tank, the grounding system tank. So what they're reading there is completely false. So, but they're not telling the customer that. The customer doesn't know. So again, so for $7,000 a day, the customer just paid for absolute garbage, and they're not telling they're not going to tell the customer that.
One other thing too, real quick, is that I was just at a plant in Florida. It's a combined cycle generation plant with a bunch of peakers there, and they had gone out and actually we had done testing for them, or SACUS had years ago. But they had been going out to Blackwood Beach, they had been going out to Hatch, they went to all these different consulting firms to do a ground study for them. And you know, we're talking price, you think that's $10,000 a day, you think that's a lot of money. Well, I went out there and did this presentation for them. They said, so you can tell us exactly what's going on the ground and everything, we want to go with this. And they held up this report they had from another person. That person never touched a meter and charged them $100,000 for that report. And they said, it's garbage. So don't get too worried about, I set expectations up front. I tell the guy, hey, you're looking at about $10,000 a day. You're looking at maybe $30,000 to test your facility, depending on the size of it. But I set that precedent up front, but then I actually make sure that they understand the value of what they're getting. And sometimes you're going to find out that there's other people out there doing stuff that cost a heck of a lot more money than we're charging. And don't be worried about that. Just talk about it up front as far as the budget. That's what I do.
Yeah, and like you said, that's what we're here for. So at that price point, if you have questions and you don't want to give an answer you're not too sure about, well, then put them in contact with us, and we'll get the process rolling, make sure that they get correct information, and then whoever the salesperson you're working with, I just have to answer some of their technical questions, and then you guys can finish off the commercial aspect, let's say.
Who are the main people from these plants that are contacting you or that you're contacting?
You're looking at anywhere from, let's say, maintenance supervisors, sometimes operations managers. It could be, what's that? Safety, yeah, safety managers. There's a number of different, we even get calls sometimes for actual design. Now, that's not necessarily in our purview. However, if you do have a customer that wants an actual ground grid design, I call up Dr. Miliopoulos, the guru, the guy, and he can do that with this. So we have a number of options that we can do with this.
You did a 4-hour one thing at BASF.
I'm sorry? Yeah, that's right. Yeah, that's right. Yeah.
Comment. Question though, my concern is, and who else has these boxes? One, and are they running around the country trying to sell the same thing we are?
Okay, this is commercially available. Smart ground testing and the WinIGS is commercially available. Now, this is going to sound like, I'm just trying to keep this within here. I can tell you right now, the learning curve is steep, and actually getting to Dr. Miliopoulos to answer his question, to your questions and everything, is highly difficult. I end up having chief engineers and such at power plants and everything because I had met them at some of the classes that SACUS would give. I keep calling him SACUS, Dr. Miliopoulos. He has, and they would be calling me because they're asking me questions about how to do the testing, and they can't get a hold of him, and they know I can get a hold of him, but I can't always just call him because he is a professor, so he has certain schools back in, and he works on a lot of other aspects. This is Smart Ground now. It's been developed at least 14 years, and unfortunately, he keeps a lot of information close to his sleeve. Yeah. So, but yes, you can get it. I've even done some work with Con Edison, and I'm out in the field doing testing, and the guy goes, "Oh, we had one of those." And I was kind of like, "Well, why am I here?" And he says, "Nobody knows how to use it."
Well, it's ongoing too. That keeping up the speed on it and so forth. You have to go back, almost like certification to keep up on that.
You have to upgrade yourself.
Yeah.
It takes a lot of analysis. You got to, so it's not just a matter of buying a $50,000 or $100,000 meter.
Well, I know the one you brought to BASF don't actually rent it from someone else.
Well, at that time they did because we had to know. Yeah, but I got utility companies that I do work with, abandoned people like that. They own equipment, never use it.
But they won't touch it.
Yeah. So there's a key difference here. Right. It depends on what you want out of it. If you want it just a meter to give you some sophisticated readings, and it can do that and everything, but you still need to know what's embedded in the meter is what's called WinSGM, just like WinIGS, but it's just for the meter. But if you really want to get in and do the analysis, let's say of the IEEE Standard 80, the lightning shielding analysis, the transient analysis, all that, you can't do that with just the meter. You need the WinIGS software. So it's a combination of the two of them. Now, if you just want to do, let's say, a testing of the tower ground impedance and things like that, a model still has to be built within, let's say, the meters software, but the sophistication, of course, goes down a little bit. So our service, what we provide, is the Cadillac, let's say. All right. Any other questions, Henry or anybody? No, we're good. Lightning Masters, I do not believe that they have the capability to do smart ground testing. Like I said, you'll see these other companies, they may have CDEGs and things like that. And a customer may bring up CDEGs, and yes, it's well known, and actually Dr. Duwalaby and Miliopoulos used to work together. They had a falling out some years back, and don't really know why, but the key thing there is ask them about the meter. How is the meter removing the noise and everything else that they have to get? How far away are they able to go for how large the facility is? Signal to noise ratio, all of those things. Good question. I'll have to look on Lightning Master to see what they have, because they do copy us quite a bit. So, but I don't think they have that. Guys, I think it's right now, it's what, 11:45? Who's up? All right. Thank you.